Gravitation is an important force. In fact, gravitation is so important that the whole universe is held together by it. The law governing the force of gravitation was discovered by Newton. As we might recall, it states, everybody in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. But have you ever wondered how Newton discovered the law of gravitation? Isaac Newton, the great English scientist, lived between 1642 to 1727. It is said that Newton was once sitting under a tree when he observed an apple falling. The fall of the apple set Newton thinking, could the force that attracted the apple to the earth also keep the moon in its orbit around the earth? He reasoned that at a point such as A on its orbit, the moon should have moved in the straight line AP according to Newton's first law of motion. But because the force is exerted by the earth, it falls back to the point B. At B, the moon would have gone along the straight line BQ, but falls back to C due to Earth's pull. At C, again it would have gone along the line CR, but it is brought back to D by the pull of the Earth. This means that the direction of motion of the moon changes at every point of its orbit. But what can a change in the direction of motion of a body mean? It means that the motion of the moon is accelerated. But what is the direction of acceleration? It must be along the radius of its orbit towards the earth, as the speed of revolution of the moon does not change. So the moon is attracted towards the earth. But why does it not fall on the earth? The reason is that the moon is in orbital motion round the earth. Had it been stationary like the apple, it would have fallen on the earth. Now, having reached so far, Newton had to support his argument by actual calculations. How did he proceed further? Newton knew that the acceleration of the apple or the other objects falling towards the earth is 9.8 meter per second square. He decided to calculate the acceleration of the moon also. It was known by his time that the acceleration acting on a body in a circular orbit is towards the center, and its magnitude is v squared divided by r, where v is the orbital velocity and r is the radius of the circular path. So, to calculate the acceleration of moon, he needed the magnitude of velocity of moon and the radius of its orbit. The radius of the moon's orbit r had by then been estimated to be about 60 Earth radii. The orbital velocity of the moon was easy to find because its time period, that is the time taken to complete one revolution, was known. If t is the time period of the moon, then the distance covered by it in this time is the circumference of the circular orbit, 2 pi r, and its velocity is v is equal to 2 pi r divided by t. So, he could calculate the acceleration of the moon. It turned out to be 0.0272 meter per second square. It is much smaller than the acceleration of the apple towards the earth, which is nearly 9.8 meter per second square. How could he explain the huge difference? Newton now turned to Kepler's third law. Kepler died 12 years before Newton was born. Kepler's laws govern the motion of the planets round the Sun. Kepler's third law says that the square of the time period of a planet is proportional to the cube of its mean distance from the Sun. Thus, if T1 and T2 are the time periods of the two planets whose mean distances from the Sun are r1 and r2, then the third law of Kepler implies T1 square divided by T2 square is equal to r1 cube divided by r2 cube. From this, he could show that the force between the Sun and the planets varies as 1 by r square. He now used the same 1 divided by r square relationship between Earth and the Moon. The distance of the Moon from the Earth is 60 times the Earth's radius. He divided 9.8 meter per second square, the acceleration of the apple, by a factor of 60 square, and he got 0.0272 meter per second square. To his delight, this was equal to the acceleration of the Moon. This convinced him that the force acting between Earth and the apple and that between the Earth and the Moon was the same. Indeed, he proposed that the force acts between any two objects. He called this force the force of gravitation. Newton's work was not yet finished. He had yet to get the magnitude of the force of gravitation. He had already found that it was proportional to 1 by r square, where r is the distance between the two objects. The difficult part was to find the dependence of force of gravitation on the mass of the body on which it acts. For this, Newton turned to Galileo's idea that the objects of different masses near the Earth have the same acceleration. Using his second law, F is equal to ma, and the fact that a is constant, it was easy to see that the force of gravitation must be proportional to the mass of the object on which it acts. What about the mass of the object which exerts the force? Here, Newton used his third law. You know this law? It states that if an object A exerts a force on an object B, then B also exerts on A a force of equal magnitude. If we take object A as source of the force and B as the object on which the force acts, then by the formula F is equal to ma, the force would be proportional to the mass of B. If we now reverse the role of A and B, that is, B becomes the source and A the object on which the force acts, then the force must be proportional to the mass of A. So, Newton found that gravitational force is proportional to the mass of the objects that interact. Therefore, the magnitude of the force of gravitation must be proportional to the product of the masses of the two objects. Finally, Newton was in a position to formulate the law of gravitation. In his published work, The Mathematical Principles of Natural Philosophy, often called Principia, Newton set down this law. According to universal law of gravitation, the gravitational force between any two objects of masses m1 and m2 placed at a distance r from each other is given by g m1 m2 divided by r square. The symbol g here is the universal constant of gravitation, and its value is 6.673 into 10 raised to the power minus 11 Newton meter square per kg square. Remember that the force is mutual. This means that m1 attracts m2 and m2 attracts m1 with a force of equal magnitude. The two forces are in the opposite direction. They form a pair of forces as required by the third law of motion. It is remarkable that though gravitational theory could not be verified at that time, there was hardly any doubt about its correctness. This is because Newton based his theory on sound scientific reasoning and backed it up with proper mathematical calculations. These qualities are essential requirement of a good scientific theory.